Hello and welcome back. The subject of this video will be to practice more with torque, since we just were introduced to it in the last video. So sort of summarizing from the last video here, torque is exerted by a force, and you can calculate torque using a new type of way of multiplying forces. It's called a cross or vector product. R cross F is how we say that. The magnitude part of this cross product for torque is going to be equal to the magnitude of the first vector, which is r, that is the distance from the axis as a vector that points from the axis of rotation to the point of application of the force, times the magnitude of the second vector, which is the force itself, times the sine of the angle in between the vector r and the vector f. The direction part of the torque, because torque is a vector, it has a magnitude and a direction. The direction part of the torque comes from what's known as the right-hand rule, and that's where you place your straightened right hand in the direction of the first vector, which is r in our case. Then rotate the hand until your fingers can bend into the direction of the second vector, which is f. Then the extended right thumb will point in the torque's direction. So this is how we find the magnitude part and the direction part of torque. Remember, we also introduced how to keep track of a third dimension when we're dealing with drawing things on a two-dimensional surface. And so we introduced these two symbols, the circle with the dot in the center and the circle with the X in the center, to distinguish out of the board from into the board. These two symbols are supposed to look like an arrow. So if an arrow is moving toward you, that means it's coming out of the board toward you, you see the tip of the arrow moving toward you. And so that's why we use a circle with a dot to emulate that. If instead you see an arrow moving away from you, then you see the crosshairs in the back of the arrow moving away, and so you see this X. So that's where those two symbols come from. So in this video, let's take a few different directions for R and F, and let's practice the right-hand rule. So let's say that we have a vector R that is pointing in this direction, and let's say that we have a force that is coming out of the board. So there's the two directions for R and F. So place the straightened right hand in R's direction. R is pointing to the right, so my straightened right hand will point in the direction of R. Now I want to rotate my hand until my fingers can flip into the direction of the second vector being F, F's direction. So notice that my fingers can't bend in F's direction with my palm facing the board. They also can't point in F's direction when my palm is facing down. They can't point in F's direction when my palm is facing upward. They can only point in F's direction when my palm is facing away from the board. Then when I extend my thumb will point in the direction of the torque. So in this case, the torque is down. So this is the direction for the torque. Let's try another example. So let's say we have a vector R that is into the board. So there's our vector R, and we have a force that is down. What is the direction of the resultant torque here? Well, again, you want your right hand in the direction of the first vector R, straightened. So R points into the board, so I want my right hand to be pointing into the board, straightened. Now I want to rotate my right hand until my fingers can flip into the direction of the second vector. Notice the only way that can happen is if my palm is pointing down. Then my fingers can point into the direction of the second vector. Then I extend my right thumb. My right thumb points in the direction of the resultant vector, and that direction is going to be now to the left. So I'm just going to move R over so that I don't end up messing it up when I draw the direction of the torque. So there's the direction of the resultant torque exerted by that force. Let's try another example. So let's say that R is this direction. So there's R, and let's say that the force is this direction. All right, so vector r is where I lie my right hand. Vector r is pointing up, so my right hand straightened should be pointing up. Now I want to rotate my hand until my fingers can flip into the direction of the second vector. That can only happen if my palm is facing the second vector. Then my fingers can bend into the second vector, and then I extend my thumb. My thumb points, notice, into the board. Into the board gets the X. So that's the direction of the resultant torque. So these are some examples of how to apply the right-hand rule. Notice, let's pretend that we don't know the direction of one of the products of the cross product. In other words, we don't know R, we don't know F, but we do know the torque. So in that case, let's say that the torque is pointing in this direction, and let's say R is pointing into the board. What direction is the force that would be exerted with a vector r that looks like this that would yield a torque like this? Well, my right thumb is going to end up pointing in this direction, yes? My palm is going to end up pointing into the board, and then my fingers extended should be pointing into the direction of the force. Notice that when all is said and done, my right hand forms a right-handed coordinate system where my palm is one vector with the knuckles of my palm being the arrow of that vector and the base of my palm being the tail of that vector r. My fingers are the second vector with the fingertips being the tip of the arrow of the force and the base of my fingers being the tail of that vector F. And then lastly, the thumbnail is going to be the tip of the torque's arrow, and the base of my thumb is going to be the tail of the torque's arrow. So your right hand forms a right-handed coordinate system, which is why the right-hand rule works. So you can see that knowing the direction of R and knowing the direction of the torque, I can find the direction of the force that yields that torque, and that is down. So I don't have to be given R and F necessarily. I just need to be given two of those three, and I can find the direction of the third. Let's practice again. So let's say we know the direction of the force to look like this, and we know the direction of the torque to look like this. So that means then that my fingers should be pointing in the direction of the force. So my fingers, when they're bent, should be in the direction of F, with again, the base of my fingers being the tail of F and the tip of my fingers being the tip of F. My extended thumb should be in the direction of the torque, with the tip of the torque being my nail, my thumbnail, and the tail of the torque being the base of my thumb. My palm then will be pointing in the direction of the vector R, with the knuckles pointing being the tip of R and the base of my palm being the tail of R. So that would be into the board. So you can see that the vector R then that would create a torque in this direction for this force would have to be into the board. So this gives you some experience at how to draw these vectors graphically to get the direction part. The magnitude part is very straightforward. Notice that this angle theta that lies between the two vectors is always going to be between 0 and 180 degrees. In other words, the only possibilities between R and F are going to be everything between them being collinear in the same direction and them being in opposite directions. So when R and F are in the same direction, then the angle theta is 0 degrees. And then the other extreme is going to be when R and F are pointing in opposite directions, and here theta is going to be equal to 180 degrees. Notice that in both of these cases, when I plug in sine 0 or sine 180 degrees, I get 0 for the magnitude part of the torque. So when R and F are aligned either collinear or completely opposing, then there is no torque being exerted by that force. Notice that the maximum value for the magnitude part of the torque will come when theta is 90 degrees. So when the angle between R and F is 90 degrees, then we have the maximum torque being exerted by that force. When the angle is anything between 0 and 90 or 90 and 180, we still have positive torque, but the torque is going to be smaller than it would be for 90 degrees. So the magnitude part of the torque will always be positive. It can be 0 for 0 degrees and 180 degrees. It doesn't make sense to have angles that are 180 to 360. They only lie from 0 to 180. And the direction part of the torque comes from applying that right-hand rule. So I think this gives us some good practice with this, and now we'll move on and actually do a couple of problems so that we can feel comfortable, and then we're going to look at conditions for both linear and rotational equilibrium and see how we can apply those to some static problems. So we'll do those two things in the next two videos. We'll see you then.